Greetings to everyone watching. Today, me and my group members will conduct a presentation for the subject ST01402 Methodology Penyelidikan dan Penulisan Saintifik for our group assignment 1. And the topic for our group is light intensity versus distance, validation of the inverse square law. Next, I'll introduce our group members. We are from the Industrial Physics course. My name is Ong Chu Xiang. And the other group members are Peter, Ahmad Airofirhan, Yuswana, and Tan Li Sheng. And next, I'll let my group members to continue with the presentation.
So hello everyone, right now I will introduce a little bit about our topic. So first and foremost, light intensity defined as the power per unit area received from a light source. It is a critical parameter in physics with application in lightning design, optical sensing, and astrophysics. The inverse square law governs the relationship between light intensity and distance from a point source, stating that the intensity decreases with the square of the distance. So as you can see the formula here, this principle is foundational for optimizing light-based technologies but can be influenced by practical factors such as source non-ideality for environmental interference. This report investigates the light intensity distance relationship to theoretical and experimental analysis, aiming to verify the inverse square law and explore its implication for industrial applications.
The research background for this topic states that the inverse square law is a fundamental concept in physics, describing how light intensity diminishes as distance from a point source increases. The relationship is important for industry like illumination engineering, where precise light distribution is needed, and remote sensing, where intensity losses affect data accuracy. And next, the problem statement for this topic state that how accurately does the inverse square law predict light intensity as a function of distance in experimental setting, and what factors influence deviation in industrial application. This report addressed this question by testing the law and analyzing its practical relevance. The objective for this research, which is to experimentally validate the inverse square law for light intensity as a function of distance. Number 2, to quantify deviation between experimental and theoretical intensity values. Number 3, to identify factors contributing to deviation from an ideal inverse square law. Number 4, to assess the law's implication for industrial application in lighting and optical system.
Next, I will talk about the literature review. So let's take a look at the inverse square law, which was described by Isaac Newton. So this law basically says that the intensity of light from a point source get weaker the farther you move from it. Especially, it's inversely proportional to the square of the distance. And the formula is I equals to P over 4 pi d square, where P is the power of the source and d is the distance from it. Now, in lab settings, scientists have tested this using photodetectors and small light sources, and it holds up really well. But in real-world situations, things can get a bit difficult. For example, large light sources like fluorescent panels don't behave like ideal point sources, and things like fog or dust in the air can scatter the light, reducing its intensity. And recent studies have looked into ways to work around these issues. One approach is using collimated beams, which are more focused and behave more like point sources. And another method is using computer models to adjust for scattering effects. Next, in practical applications like lighting design, this law helps engineers figure out how to place light to ensure even brightness. The Illuminating Engineering Society even uses it as part of their standards. But the key takeaway is that while the law gives a strong foundation, real-world use requires tweaks and testing to make sure it works effectively.
Hello everyone, my name is Suhana binti Rahmat, matrix number BS23110170. So I will talk about methodology part. This study employs a combination of theoretical modeling and experimental validation to investigate the light intensity versus distance relationship. The inverse square law was used to calculate expected illuminance values using formula I equal to P over 4 pi d square, assuming a 5-volt LED source. Calculations were performed for distance of 0.1 meter, 0.2 meter, 0.5 meter, 1 meter, and 2 meter. The experiment was conducted in a dark room to minimize ambient light. The photodetector was positioned at distance of 0.1 meter, 0.2 meter, 0.5 meter, 1 meter, and 2 meter from the LED. Illuminance was measured 3 times at each distance, and the average was recorded. Experimental illuminance values were compared to theoretical prediction, percentage deviation were calculated, and potential causes were evaluated. Thank you.
Hi everyone, my name is Tan Dishan, matrix number BS2311016, and now we are going to look at the results and discussion part. So look at the results. The experiment measure illuminance at specific distance, and we compare the results to the theoretical predictions based on the inverse square law. So the table 1 summarizes the theoretical and experimental illuminance and also the percentage deviation. So here we got 5 different distance, that is 0.1 meter, 0.2 meter, 0.5 meter, 1 meter, and 2 meter. And we record the theoretical illuminance, the total lux where the experiment is going, and we also calculated the experimental illuminance by using the formula given and also the percentage deviation. So at 0.1 meter, the percentage deviation is about 4.52%. It's also same with the 0.2 meter, but at 0.5 meter, the percentage deviation is 4.40%, while at 1 meter, the percentage deviation is about 4.52%. It's also same with the distance at 2 meter. So now we look at the figure 1. There's a graph shows the relationship between illuminance and distance as we comparing the theoretical and experimental data. So as the distance is increased, the illuminance is decreased. So the experimental data closely follow the inverse square law with deviation of about 4.4% to 4.52%, as we show at the table 1 just now. So the deviation is slightly larger at the 0.5 meter, possibly due to the minor alignment error in the photodetector. So now let us look at the discussion part. So the table and graph confirm that light intensity decreases with the square of the distance, validating the inverse square law in a control setting. The experimental illuminance values are consistency with 4 to 5% below the theoretical predictions, likely due to the LED's non-ideal point source behavior, for example the finish size and minor ambient light interference at larger distance. So these findings align with the literature, which notes that the real-world systems deviate from the ideal model due to the practical limitations. So in industrial context, the inverse square law is critical for optimizing light-based system. For example, lighting designers use the law to calculate the luminary placement for energy efficiency illumination, it ensuring the brightness while minimizing the power consumption. So in remote sensing, understanding the intensity for off enables accurate calibrations of optical sensors over long distance. The logarithmic scale in figure 1 highlights the rapid drop in intensity. This emphasizing the need for precise source positioning in application, that require high illuminance. So to address deviations, industries can use collimator source, for example, the lasers or software corrections for environmental factors like scattering. So the results underscore the inverse square law's robustness while highlighting the importance of accounting for non-ideal conditions in practical applications.
So to conclude our topic today, this report experimentally verifies the inverse square law for light intensity as a function for distance. Demonstrating that illuminance decreases with the square of the distance, the experimental result presented in Table 1 and Figure 1 show close agreement with theoretical predictions with minor deviation for about 4 to 5% attributed to the LED's finite size and environmental factors. These findings are significant for industries like lighting design and remote sensing, where the law guides system optimization. To enhance applicability, industries should consider advanced light sources or correction algorithm to mitigate deviations. Future research could investigate the law's behavior in scattered media with extended sources to further refine in industrial application. This study reaffirms the inverse square law as a foundational principle for light-based technology in the physics industries. That's all from me. Thank you.
And these are the reference for our poster, and that's all for our presentation. Thank you.